Today's lesson is on CSEC chemistry, where we will be focusing on organic chemistry. I am Roger Dawkins, a teacher at the St. Hugh's High School. All right, so we left off the last time at alkenes, right? Remember, we looked at alkanes, where the carbon-to-carbon double bond is a single bond, and we moved on to alkenes, right? And so we're going to continue where we left off today. Now, if we turn to the slide, all right? So as you can see from the slide, we're going to be touching on alcohol today. So it says normal college students spend their weekends with this kind of alcohol, but as a chemistry student, this is the kind of alcohol we will be focusing on, all right? So just to recap, alkanes are organic compounds that have only carbon-to-carbon single bonds, right? So if you look at your organic compound and you're only seeing carbon-to-carbon single bonds, that means it's an alkane, all right, one with the A. So alkanes undergo mainly three types of reactions. Cracking, that is where you convert a large alkane to two smaller alkanes, or a smaller alkane with an alkene. All right, remember, cracking always produces at least one alkene. All right, substitution, where you are replacing a hydrogen atom with a next atom. All right, it can be a halogen, right? And that's how you end up with haloalkanes. And the last one is combustion, where you're burning your alkane. Now remember, whenever you burn alkanes, it burns with a nice, clean blue flame. You don't get that kind of dark, sooty flame from it. All right? So alkenes are organic compounds that have the carbon-to-carbon double bond. All right? And they undergo mainly two types of reactions that we're going to touch on today, which is combustion and addition. All right? So, combustion of alkenes. When you take an alkene and you burn it in excess oxygen, you're going to get carbon dioxide and water. All right, and here's a general equation for it. In this example here, we're using ethene and we're using oxygen. All right, and you're going to get carbon dioxide and water. Remember, whenever you're doing a chemical equation, please make sure that you balance your equation. All right, so ethene burns in oxygen as excess oxygen to give you carbon dioxide and water. And here we can see a comparison between burning an alkene and an alkane. So on the left side of the screen, we're burning an alkene. And as you can see, the characteristic dark, sooty smoke coming off the fire. The reason for that is because alkenes have a lot of unreacted carbon in them, right? So when you're burning an alkene, there's a lot of unreacted carbon, and that translates as this dark, sooty flame. While alkanes, the one with the A, remember that, all right? So alkanes, now when they burn, it's nice and blue because there's no unreacted carbon atom. All right, I hope we're getting that and we understand what we're saying. All right, so we're going to look at addition reactions. Now, we will consider a few addition reactions of alkenes. So the first one we're going to look at is hydrogenation. As you see the name hydrogenation, that means you're going to add hydrogen, right? So alkenes react with hydrogen in the presence of a finely divided nickel catalyst at a temperature of about 150 degrees Celsius to produce the corresponding alkane. Now, we all should be familiar with what a catalyst is, right? These are substances that alter the rate of a reaction. So they can either speed up the reaction or they can slow it down, right? But most catalysts that we use, they speed up the rate of a reaction, right? And they do this by lowering the energy requirement for the reaction, all right? Now, as you should know, we have biological catalysts inside of us known as enzymes, and those are the things, are the substances that help us to live on a day-to-day basis. They reload the reaction for digestion, for many different reactions in our body. All right. So here we have alkene and we're adding hydrogen to it. So if you look at the bottom of the screen, right, you see a nice alkene structure and you see a hydrogen structure. Now I've highlighted the hydrogen in red to show you where it's going to end up once it combines with the alkene. So in the presence of the catalyst and at 150 degrees Celsius, hydrogen is added to the alkene structure to form an alkane. So ethene is converted to ethane. All right? So ethene is converted to ethane. All right? And it's called an addition reaction, of course, because you are adding things to the alkene structure. All right, now hydrogenation is not really used to produce alkanes. It can do that, but we're not really used for that because there are more productive uses for alkenes. However, it is quite important in the processing of butter and margarine. All right, so when you like to spread that butter on your bread, right, or on your bagels, right, we use hydrogenation in the process of making butter and margarine. All right. So now we have alkenes and they're going to be added with hydrogen halide. So once again, you see the hydrogen and the halide, that means it will contain a halogen and hydrogen. So in this reaction, the hydrogen halide will be added across the double bond, thereby producing the corresponding haloalkene or alkyl halide. Now remember, don't be afraid of the words, right? When you hear haloalkene, halo comes from halogen, and alkene is an alkene group. So when you hear haloalkene or haloalkene, because some people pronounce it different, it simply means that there's an alkene with a halogen in it or attached to it. All right, so here we go. So here we have our ethene molecule, and we're going to add hydrogen bromide. So that is our hydrogen halide. All right, so ethene plus HBr, and we're going to end up with bromoethane. All right, going to end up with bromoethane. So bromo means, come from the word bromine. All right, so you end up with a halo or a haloalkane. All right, next one is hydration. Hydration means that you're going to add water. So when you feel hydrated, it means that you're well, you have a lot of water in you, right? So when you hydrate something, you're going to add water to it. So alkenes undergo an addition reaction with water in the presence of a catalyst to form alcohol. All right? So this type of addition reaction is called hydration. All right? I hope you're following. All right? So in this process, ethene and steam are passed at 300 degrees Celsius, quite a bit high of a temperature, and a pressure of approximately 60 times atmospheric pressure, right? So imagine what you're feeling, the regular weight of gravity that you're feeling now, and estimate that gravity increases by about 60 times. That's how much pressure this reaction needs to undergo to react. All right, so with a pressure of 60 times above atmospheric pressure over phosphoric acid catalyst, you will end up getting ethanol. All right, so here we see ethene again, right? Ethene is our standard when we're trying to explain alkenes. So ethene with water, you're going to end up with the corresponding alcohol. Corresponding means that you're going to keep the same name, but you're changing the homologous series. So ethene will become ethanol. If it was methane, we didn't know methane. If it was propene, it would have become propanol, and so on, right? So the alkene is converted to the corresponding alcohol. All right, so these are fairly simple. Once you understand the concepts, you can actually tackle these questions fairly easily. All right. Now, we use alkenes to manufacture or to produce alcohol. So here we have ethene and steam. Steam, as we know, is just hot water that's vaporized, right? So ethene and steam will go into a reactor at 300 degrees Celsius, as we said before, at 60 atmospheric pressure. Now, the phosphoric acid catalyst will cause them to react, and you will get ethene, steam, and ethanol. Then, these are run down into a condenser, right? And the condenser now will cool the gases back below their boiling point. So it will convert them back to a liquid. So in the reactor, they're going to be gaseous, and when they go into the condenser, they become a liquid, all right? And then once they have been liquefied, then they will be sent down into the separator. And as we see here, the separator will send the water and ethanol on its way, while unreacted ethene will be sent back to the reactor. Now, this part is very important because on a regular basis, the reactor does not convert enough of the ethene to ethanol. Actually, only about 5% of the ethene is converted to ethanol, right? And that's very wasteful. And so to combat that wastefulness, any ethene that's not reacted is sent back into the reactor to undergo the process again. And by doing that, you're able to extract about 95% of the ethene and convert it to alcohol. All right, so that's a very simple diagram to understand. Just know that ethene and steam reacts in the reactor, then those are condensed back to liquid, and then the ethanol and water is sent on its way, while the unreacted ethene is sent back to the reactor because we don't want to waste. All right, so now we're going to look at the addition reaction of acidified potassium manganate. All right, so alkenes react with acidified potassium manganate solution. Potassium manganate solution, 7 solution, is a strong oxidant, right? And will initially convert the double bond to 2 alcohol groups. The purple color of the permanganate will fade as the reaction proceeds. All right, so here we have ethene, we have water, and we have the oxidizing agent. Right, so the O here is coming from our potassium manganate. We just don't put everything because only O from that compound is important. All right, and you end up with ethan 1,2-diol. All right, so just to see where we get that name from, all right, so we have OH, OH, and then we put in our hydrogen. All right, so on the screen it said ethan 1,2-diol. Now, how do we get that name? All right, so remember, the functional group of an alcohol is the OH group, right? So here is a functional group, here is a functional group. So those are your functional groups for your alcohol. And the carbon that's closest to the functional group, that is denoted as carbon 1. All right? But because we have 2 alcohol groups, it doesn't matter where we start. If we start here, 1, 2, 1, 2, same thing. All right. So ethan, because the main part of it is 1, 2 carbon and it's a single bond. All right? So we would have eth, because again it's a carbon to carbon single bond, and the 1, 2 means that it's attached to carbon 1 and it's attached to carbon 2. So that's how you end up with the 1, 2, and then remember your alcohols end with a null. All right, alcohols end with a null, and so because there's 2 alcohol groups, it's going to be diol. All right, so the anol is right there, but you're adding the 1,2-diol in between, and that's where you get the name from. All right. All right, so let's distinguish now between alkanes and alkenes. Now, alkenes will react with acidified potassium manganate, as I just said in the previous slide. And the alkene will change the purple solution to colorless, right? So you see that purple color disappearing as it reacts with the alkene. Alkanes do not have this kind of reaction. Alkanes do not react with acidified potassium manganate solution. All right, so this is one test you will do, or you can do in the lab, to distinguish between an alkane and an alkene. All right. Now the second one that we can use is bromine water. That's just simply bromine gas, you dissolve it in water, right? So when bromine water is added to an alkane solution and shaken, it will still be brown. No reaction happens, all right? But when you add that bromine water to an alkene and shake it, the bromine starts becoming colorless, right? So the bromine water will react with an alkene and get a color change, while the alkane will not produce a color reaction. All right? So as you can see in both examples, what we're looking for is that the alkene is causing a color change to the reactant. All right? So these are 2 ways we'd use in the lab to distinguish them, right? So if we were still at school, we would have encountered this by now for our 11th graders. All right. So now we're moving on to alcohols, and these are the organic molecules that contain the hydroxyl functional group. Remember that is our OH group. All right. So let's get to the board. So alcohols. So let us recap. All right. So they end with anol. All right. That's what they end with, anol. So methanol, ethanol, propanol, butanol. Right. They contain their functional group. So functional group is the OH group, right? This is known as the hydroxyl group. All right. So this is known as our hydroxyl group. All right. And remember, whenever we're naming our alcohol, we begin at the carbon closest to the OH group. All right, you start with it closest to the OH group. All right, and that's how we get our isomers for alcohol. Because when the OH group changes, right, when the OH group changes, we get isomers of alcohol. All right, so let's look at some isomers. So now, so 1, 2, 3, all right, 4. We're going to add on our hydrogen, our alcohol. So we're going to add the OH right here, H, H. All right. So remember, we start counting from the carbon that's closest. So we have 1, 2, 3, 4. No, because this carbon is not close to this carbon. So actually start counting here. 1, 2, 3, 4. So this is carbon 1. And so this alcohol would be 1, 2, 3, 4 carbons, which is butanol. And the position of the OH group is on carbon 1. So 1 butanol. All right. If I took the OH group and shifted it over here. All right, so 1, 2. So now this changes to 2 butanol. All right, and so that's how we get our isomers. We can also use branching, but with the same thing it follows, same rule it follows. All right, so alcohols are organic molecules containing the hydroxyl group, and their chemical reactions occur mainly at the functional group, which is the hydroxyl group. All right. So here are 2 examples of alcohols. We have propan-1-ol and we have 2-methyl-propan-1-ol. All right, so if you look at the 2-methyl-propan-1-ol, the functional group is on carbon 1, right? The rightmost carbon, that is carbon 1, which means the methyl group, right? The methyl group, the carbon that's going up in the air, is attached to carbon 2. And that is why the name is 2-methyl-propan-1-ol. All right? Great. So alcohol reactions now. So alcohols also undergo combustion, which means they can burn alcohols. I'm sure we know this, right? Just like alkenes, alcohol burn with a clean blue flame, right? And it also produces carbon dioxide and water. And as we see here, is a general example of an ethanol being burnt in oxygen. All right, and so you get carbon dioxide and you get water. So dehydration is the next reaction of alcohols, right? So remember, when we look at alkenes, we said hydration is adding water, which means dehydration is the removal of water. All right, it's very simple. So when you remove the water in the presence of a catalyst, you'll get an alkene and water. All right, the reaction removes the hydroxyl group from the alcohol and a hydrogen atom from an adjacent carbon atom. So let's look at an example here. So again, I put the hydroxyl group and the hydrogen in a different color to show what's going to be removed. So the OH group is removed and the hydrogen atom that's right beside it is also removed. And so the carbon and carbon will form a double bond and end up with an alkene. So dehydration will always produce an alkene and water. All right? And so here's our reaction right here. All right. So alcohols also react with sodium. We're using ethanol here. So if a small piece of sodium is dropped into some ethanol, it reacts steadily to give off bubbles, and we call that effervescence. All right, effervescence just means bubbling, right? So anytime you see that on a test, don't be afraid of the word. Effervescence simply means bubbling. So it will give off bubbles of hydrogen gas and leave a colorless solution of sodium ethoxide. All right, and so we see the chemical or the compound right here. So on this side, we have ethanol reacting with sodium, and you get your sodium ethoxide and hydrogen gas. All right, so it will produce a reaction like this. So if you have an alkene, an alkane, and an alcohol, but you don't know which is which, if you drop some sodium in that solution, right, and it's a bubbling, then more than likely it's an alcohol. All right. So oxidation and esterification, that's also reactions of alcohols. So upon oxidation with strong oxidizing agents, right, and high temperatures, alcohols will completely oxidize to form carboxylic acids. And remember, carboxylic acids are also another group of organic compounds, right? So the common oxidizing agent used is potassium permanganate. All right, potassium permanganate is our regular oxidizing agent. Now, if we remember from redox reaction, right, an oxidizing agent itself becomes reduced. All right, and what we mean by reduced, we mean that it has either given up oxygen or taken up electrons or taken up hydrogen. All right, so we see the reaction here on the board, on the slide. Ethanol in the presence of potassium permanganate and sulfuric acid at 100 degrees Celsius will produce ethanoic acid. So oxidation will produce the corresponding alkanoic or carboxylic acid. So ethanol, ethanoic acid. Propanol, propanoic acid. All right? And esterification, we won't go into great details with that because that's a topic for itself. But basically just know that an alcohol is reacted with a carboxylic acid in the presence of an inorganic acid catalyst, right? All right, so we can look at some past paper, but I'm going to go back over a few more things, right? So with our alcohols, one of the next thing we need to remember, right, is the general formula, which is CnH2n plus 1 OH, right? So that is the formula for our alcohols, right? So let's say an alcohol compound has 5 carbons, right? I want you to find out the chemical formula. So we say N, of course, is the number of carbons. So C, 5, H2, I put a 5 in bracket, plus 1, OH. So you're going to end up with C5, 10, plus 1, OH. So our final answer is C5H11, OH. All right, it's not difficult. So again, let's do our next practice one. So let's say it has 8 carbons. So 2, Same principle apply. C8 H28 plus 1 OH. So you're going to end up with C8. 28 is 16. And so your final answer is C8 H17 OH. All right? So fairly simple. All right. Now, let us look at the naming of the larger alcohol compounds. So let's see, C to C to C. All right. All right, 1, 2, 3. So the OH group, I'm going to put it here. All right. So the OH group is here, which means we're going to start counting right here. So this will be carbon 1. All right. So let's count now. Now what is the straight chain? We can say 1, 2, 3, 4, 5. Or we could say 1, 2, 3, 4, 5. Right? So since I'm getting the same thing, I'm going to keep the straight chain as this one. So 1, 2, 3, 4, 5. So it's going to be pent. So pent, it's 5 carbon, and it's an alcohol, so anol, right? And the hydroxyl group is on carbon 1, right? And now the final thing is to look at the alkyl group. So remember, our alkyl groups end with YL. So how much carbon is right here? It's 2, right? Which means it's going to be ethyl. So we're going to have, on which carbon is it on? Carbon 1, carbon 2, carbon 3. So now we're going to have 3 ethyl, 1 pentanol. Or, as I said, you can rewrite it to be 3 ethyl, pentan, 1 all. All right? Fairly simple. So we're going to look at some past papers now. All right? So the first one says, the following diagram shows the structure of compound R. And we see a compound R here. And it says, state the name of compound R. So first thing we need to do, let's draw this out. All right, so I'm seeing 1, 2, 3, 4, 5 carbons. So it says 1, 2, 3, 4, 5 carbon. So we have 3 CH2, 2 CH, and this should be CH3, right? Okay, and the alcohol group is here. So how do we name this? Remember again, we're going to start at the carbon closest to our functional group. So obviously this carbon over here is very far, so we're going to start on this side. So 1, 2. So the hydroxyl group is on carbon 2, all right? And since it's a straight chain, right, we don't see any branch, so we're going to put the 2 there. And again, 1, 2, 3, 4, 5 carbon. So it's going to be pent, and it's an alcohol, so it's going to be pentanol. All right? Simple, easy 1 mark. All right, second one says, state the conditions required for the dehydration of ethanol. All right? Now, we should remember that the dehydration of ethanol is when you're removing water from the compound. And so, this will require a temperature of about 180 degrees Celsius, right? And it will also need concentrated sulfuric acid as a catalyst. All right, so that's your 2 marks. The concentrated catalyst, acid as a catalyst, and the temperature of 180 degrees Celsius. Some books may have it as 170 degrees, right? So 170, 180, and you will still get your answers or your mark for that question. All right, so I hope we understood that one. So the second question says, The structure of 3 organic compounds are shown below. We have compound A, compound B, and nice compound C. So it says to state the name of the homologous series to which each of compound B and C belongs. All right, so let's look at compound B. So what I'm seeing here, all I'm seeing is carbon and all I'm seeing is hydrogen. Nothing more, nothing less, right? And all the bonds between the carbons are single bonds. There's only one bond line. So that means compound B very easily is an alkane, all right? Alkane. So compound C now, I'm seeing an OH group, right? So some person might jump and say alcohol, but no, we have to remember that there's also a C double bond O group right there. So let me come to the board. So we did not do carboxylic acids, but we touched on it when we began organic chemistry. So we say C to C to C, O, OH, right? All right, so even though this is there and you might jump onto alcohol, we have to remember that this is there as well. And there is a homologous series that does have COOH, right? And that is your carboxylic acids, all right? So this compound belongs to the carboxylic acid homologous series, or the alkanoic acids, all right? So B alkane, C is carboxylic acid or alkanoic acid. So compound A now, it says burns with a blue flame in oxygen. All right, so compound A has 2 carbons and an OH group. So that means, so let's look. So 1, 2, OH. All right. So there's no double bond O in this. So it's a straightforward alcohol. Ethanol to be exact. All right. So let us say now. So how much carbon? 2. So C2, 1, 2, 3, 4, 5, H5, and then OH. And we are going to react that with oxygen, right? Because we are burning. And so we're going to end up with carbon dioxide plus water. And now we begin to balance. Right, I like to balance beginning after the arrow. All right, so we have 2 carbon on this side, we have 1 on this side. So we're going to put a 2 here, right? So let's go to the hydrogen. There's 5, 6 on this side and 2 on this side. How do we convert 2 to 6? Right, you multiply it by 3. So we're going to put a 3 right there. All right, so all that's left is the oxygen. There's 2 oxygen on this side, 2, 3, and this has 4 and 7. All right, so how do we balance that? We can put a 3 here in front of the oxygen. All right, so 3 2s 6, and the 1 here would be 7. So 7 oxygen here, 7 oxygen here, and it is balanced. All right, so liquid, gas, gas, gas. All right, students always seem to forget their state symbols when you're doing balance equation. Please do not leave them off. All right, they add to your marks. All right, so here is our balance equation for the question part B. Right, all right, it says describe what you would observe when bromine solution is added to ethene, and it must give a balanced equation. All right, describe what you would observe when bromine solution is added to ethene. Now, if we remember between our in our distinguishing test for alkanes and alkenes, right? Alkenes will decolor bromine. All right. So what you would observe is that the bromine solution would change color over time and become colorless. All right. And so ethene, right? C2H4. And you're adding bromine, right? And bromine solution, it would be in the aqueous state. And you're going to end up with C2H4Br2. All All right, because what's happening again, C plus the Br, and then you're gonna get your haloalkyl, right? Or haloalkyl. So C to C, and the bonds open up. So H. So you still have your 4 H's, but now the bromine is being added to the structure. All right. So now you will have 1,2-bromoethane. All right. So 1,2 again because it's on carbon 1 and on carbon 2. So 1,2, in fact, it will be dibromoethane because it's 2 bromine. All right. So B says to give the name and fully display structural formula of 3 straight chain isomers of pentanol. Pent 5. All right. And since it says straight chain, that means we cannot, we're not supposed to branch it. So pentanol. So let's look. Pent means 5. All right. So 1, dot. So pentanol. So the first one, that. All right. And so since the hydroxyl group is on carbon 1, this would be pentan 1 all. So that's the first isomer, pentan 1 all. All right. So the second straight chain isomer, so we're going to get back our Ca to C, 3,5, right? And remember, alcohols can form isomers in the straight chain format by moving the hydroxyl group. So all I'm going to do, take this hydroxyl group and move it over to carbon 2. All right, same thing, fill in the H's. And then you'll end up now with pentan 2 all. All right, and we can see where this is going. For the last one now, because it says 3, again, I know it's a little bit tedious, but let's hold it. All right. Again. So now I have moved it here, and I'm going to move it here on the 3rd carbon, OH. All right. So what you do again, you fill in your hydrogen. And now, the name of this compound, because it's on carbon 3, will be pentan 3 all. All right? So, those are our 3 isomers, straight chain isomers of pentanol. All right? Now, it's not a part of the question, but I want to draw the line structure, right? Because I know that some person might have forgotten about that. Remember, when we say line structure, it means that when you see something that looks like this, those things, right? So remember, every kink represents a carbon. So it's 5. So you can say 1. So the first one will be up here. 1, 2, 3, 4, 5. All right, see? So carbon 1 will be here. 2, 3, 4, 5. Or since we detain it the other way, let's renumber this. All right? Because I put the OH group over here. So this would be 1, 2, 3, 4, and 5. All right? So the OH groups attached here. So all it will do is just simply put OH. All right? And this is the same thing as this. All right? This is just a shorter, condensed version of it. All right? So we're going to wrap up here for today, but what I'm going to do, I'm going to leave this last question on the slide with you. Right? So screenshot this, take a picture, or do what you need to do to get this question off. It says, which of the above would decolor acidified potassium manganate solution? And then once you answer that question, all you need to do now is state which of the above would react with sodium to form a salt and draw the balanced equation. All right? So I said screenshot it, take a picture, memorize it, do the question, right? Push yourselves. There are many more questions online, all right? And so that's all for today, all right? For CSEC chemistry, organic chemistry. And, we hope you grasp some of the concepts of the points that we discussed. Until next time, I am Roger Dawkins.